Guys, good afternoon to everyone. Today we have Hector Olivares from Radboud University in Nijmegen, in the Netherlands, that is going to join us soon in our group. We don't know yet when, but so feel free to listen to his talk and ask him questions during the talk, and or even at the end, while you feel more comfortable. And today he's going to talk about how magnetodynamic hydrodynamics can be used to study gravity and strong gravitational systems. Thank you very much.
Thank you very much. Well, thank you all for the invitation and for the opportunity to talk here. I will start by saying that this time is a, why doesn't it change? It already changed in my, okay, it's good. So I will start saying that this time is a great and special time for us that study general relativity and compact objects. There have been amazing experiments like well, the detection of gravitational waves, the images generated by the Event Horizon Telescope. So, and we can see also this by looking that some of the recent Nobel Prizes have been awarded in topics related to general relativity. And the most interesting thing about this is that there is more to come. So this fact that there is more to come, we know because we know that there is also, in addition to confirm the prediction of general relativity, we also need that ultimately general relativity is not the ultimate theory. We know that there are some more things to find, and that we need to. Okay, now it has updated. So
There's a lag.
yes, so indeed, so we know that general relativity is not the ultimate theory. There are more things to discover, and if we explore a new regime, it is more likely that we will find some of these new phenomena that will help developing the theory that is beyond general relativity. So we know that this is needed because there are problems that are not completely solved in the standard model of general relativity plus the standard model of particle physics, like the dark components of the universe, what causes inflation, and there are also well problems from the pure general relativity quantum gravity side, like the non-renormalizability of gravity or the black hole information paradox. And as the title of my talk suggests, I will be talking about how MHD can help us, well, explaining or interpreting these new phenomena that we could potentially be observing. And there are three main ways in which this could happen. So first, and probably the most obvious one, is that any extension to fundamental physics must interact with the universe, and the universe is full of plasma. So we need to account for this. Plasma is described by the questions of general or by the questions of magnetohydrodynamics. So we need to account for this. Another topic which is very interesting, but I will not treat in this talk, is that there are some predicted hypothetical phenomena that have analogies in plasma physics. One of these is superradiance, and this is very interesting to talk about, but maybe, well, as I said, I will not cover this topic. But another topic that I will cover in this talk is this last one. So there are methods that were developed for computational magnetohydrodynamics that actually could also benefit from being applied to other fundamental physics that are described by differential equations. In particular, I will speak about how magnetohydrodynamics techniques can be applied to the numerical solutions of the Einstein equations and give some benefits or potential benefits. So, well, regarding the first point, I just want to show you this slide that we should start soon. Okay. It's almost there, okay. So, well, so just to, if we think of something as simple as a black hole, well, as a black hole shadow, in our minds, or normally if we think of it as theoreticians, black holes are very clean objects. They have a shadow that should have a very specific relationship with their mass and their spin. But in practice, if we try to look at it and measure it in a realistic environment, so surrounded by plasma, we will see that there are many ways in which you could completely miss a shadow or measure a wrong size for it. So, and these are represented in these four panels that are here. So these are from a paper that we published in 2020. Thomas Ronzauer is a colleague from Nijmegen and is the main author. So here, well, this is a almost perfect case in which you completely see the shadow, and the size of the central brightness depressions corresponds to exactly to the size of the ring that you can that can be seen. Here in all of the panels, the dashed line is the actual size of the shadow of the black hole. But it can be that, for example, the plasma is optically thick at the frequencies at which you are observing, and then you can completely miss the shadow. It can also be that for some reason the distribution of luminosity is slightly outside, so it's not always increasing when radius is decreasing, and you have the maximum luminosity located far away from the event horizon. In that case, you can have the length image of the ring of maximum luminosity exceed the predicted size of the shadow, and you are in this case. And finally, there is also this possibility in which there is a lot of Doppler boosting from one of the sides of the image. And if you try to look at it with the resolution of the Event Horizon Telescope, you would probably just see a bright spot here, but no trace of the ring-like structure of the shadow. So, well, fortunately, also from the conclusion of this paper is that if the emission is optically thin, this could in principle allow for measuring the shadow size of with an accuracy of 5% for the conditions of the Event Horizon Telescope, which are very good news. And what are better news is that the predictions that we do on geometry of the spacetime and on the behavior of plasma physics close to the black hole are now becoming testable. In fact, there are several things that we already know and that we found from the observations of the Event Horizon Telescope. So, for example, I listed here some of the most interesting things that we discovered regarding the accretion flow from interpreting the images of Sagittarius A star and M87. For M87, we know that the spin is likely non-zero, but we already knew from the powerful jets. But from modeling with MHD simulations, we also found that it is most likely that the accretion state is what is called a MAT, or a magnetically arrested disk, which means that it is in a regime where magnetic fields are very strong, they're dynamically important, and they regulate accretion. We also know that most likely the jet is powered by the blunt force Nagel process, because this is those are jets that are powered by via this mechanism are those that explain the high luminosity of the jets that come from M87 star. And for Sagittarius A star, modeling from the HT allows us to say that the spin is likely positive, and it is less or equal than 0.5. That the accretion state is also probably a MAT. We know also from our modeling that the inclination is smaller or equal to 50 degrees. That the spectrum is more consistent with a jet-like emission than with a disk-like emission, even though we don't see a jet for Sagittarius A star. This is what the spectrum says. And there are some caveats, and the most important one is that we are having difficulties modeling the variability. So all of our simulations or most of our simulations are more variable than what they should, in order to explain the small variability of Sagittarius A star. From the point of view of geometry and of gravity, probably there are less things that we can say, because we need more accuracy. But there are a few that came out of these observations with the Event Horizon Telescope. One that is very important is that the size of the shadow is consistent with that of a clear black hole over 3 orders of magnitude, because M87 is 1,500 times more massive than Sagittarius star, and for both of them, we see that the black hole shadow is what is predicted for a black hole of that size. If we consider that, well, also general relativity has been tested and is completely consistent with data also for the gravitational wave observations. These are at a very different mass scale, and so we seeing no changes over this big span in length scale will allow us to say that probably gravity has no characteristic length scale over 8 orders of magnitude, which is a very big result. Also, well, from the measurements of the shadow size are not as precise as to tell us still a lot of things like whether there are some generalized charges or what is the spin of the black hole, because the deviations that we see are roughly 10%. Oh, sorry, I didn't mean to change that. Yes, but in principle, when we increase the precision or the resolution of these observations, we just need a slight increase. Now the fractional deviation, or potential for detecting a fractional deviation from error is only of 10%. But if we get to a 7%, in principle, we could already start saying something about the spin. And also, well, something interesting that was done for the last series of papers for Sagittarius star is that at least for the first time, we consider some specific alternatives to curved black holes. This includes, for example, the model for boson star on which I worked together with colleagues from Frankfurt some years ago. But even though it is still not possible to say something very general about these models because there are very specific alternatives, well, it is a good starting point to at least consider some of these alternative solutions. So, but well, another thing that is very interesting to say is how these models are tested. So what do we do? What is the pipeline that we follow in order to compare predictions to observations? And well, it turns out that there are many ingredients that are necessary. So as I mentioned, in order to compare things with actual observations, there are several layers that need to be taken into account. So we first, from the clean space-time model that one can think of, one has to put on top first the layer of plasma dynamics, then also the layer of radiation dynamics, because, well, radiation also has a lot of complexities and is also affected by a curved spacing. And again, we also need to take into account uncertainties associated with the observation instruments and the observing conditions. Fortunately, for Sagittarius star and M87, the physical conditions allow to decouple all of these steps. So the fact that the supermassive black hole is, well, extremely heavy, and while the accretion flow that surrounds it is extremely dilute, having like of order of 1,000 particles per cubic centimeter, allows to decouple the space-time from the plasma physics. So plasma, whatever it does, will not back react into the metric in an appreciable way. Also, the fact that these plasmas are well, very dilute and hot and optically thin allows to decouple radiation dynamics or general relativistic radiative transport from the plasma dynamics, so that one can make a relatively small library of plasma simulations, and then, well, making in post-processing the simulations of radiation dynamics in order to create a library that expands a much larger parameter space. And well, observations is of course decoupled from the other step, because there is no way in which we can influence the the system. So, well, this is how well all the process that is used. From here to here, we can either compare simulations in the visibility space, that is what we actually measure, that is the Fourier transform of the image, or some things can also be compared in the image element space. So from all of these steps, my work has been mainly in this stage, that of plasma dynamics, and I will now will show you some more details about the code on which I work that was used in part to generate this library of simulations and some specific applications of what can be done. So this code that I contributed to. So this code that I contributed to code during my PhD is the code back, or the black hole accretion code. You should see the slide in little time. Okay. So this code solves the equation of general relativistic ideal magnetic hydrodynamics in a fixed spatium. Well, it is based on an older and reliable code that used to do Newtonian MHD and also special relativistic MHD. It has a nice parallelization. It can run on 10,000 of CPUs, and it has adaptive memory refinement, which is what you see here. It can increase the resolution in some specific places where the simulation becomes more challenging. It is public. We can download it. You can download it from this website. And we try to keep it well documented with manuals and tutorials. So, in fact, one of these tutorials tells precisely about how to add arbitrary spacings to make simulations on them. Well, we will see it soon.
It happens even if you go from your laptop directly. It's lagging even if you go from your laptop, or it's only the.
No, it is lagging. So in the laptop it has updated. So it is just lagging from here to from presentation to the screen. So well, I will go just quickly through this. So you can add arbitrary time-independent metrics. This can be either numerical or analytical. There is no need to calculate derivatives or connection, because that is done automatically by the code. One can use also tabulated metrics. And recently, even if it is not in the published version, but if you want to have it, you can ask me. It is coupled with a spectral solver KDAP that allows to generate some spatium that fulfill the constraints of general relativity. So, as an example of how this can work, and we try to keep it simple and let's say suitable for interesting student projects. I will show you some applications.
Sorry, can I ask a question? What do you mean with the coupling with KDAP? So KDAP is a library for initial data.
That's correct. So one can generate initial data with KDAP and then use it as a background, as a spatial background for a simulation in back. Okay,
but you're not involved in the metric.
No.
So you use that as a prescribed metric.
Exactly. Yes. I will show a bit more of this in another slide. So this is one project. This is an example of a very exotic spatium, and it is a spatium of a warp drive. Solution for hyperfast travel without violating general relativity by Miguel Alcubierre in 1994. So, this is Daniel Vickers. He's a student that is doing his bachelor project at Radboud University, and he is trying to answer the question of what would we see if one of these objects passed close to us in the solar system. So this is more a fun project than anything, but in principle it has a potential for detecting if there are advanced alien civilizations that are making use of this technology, even if we don't know how to use it. But these are some examples of simulations. So this is a warp bubble passing through a relatively cold medium, like the local bubble of the solar system, and this is one passing through the solar corona and producing a nice shock cone. So the idea is that one could read light pools. They should be characteristic, and then one in principle could find out whether this passes by us.
So why do you produce a shock wave in the first case, not in the second?
So producing a shock, the opening angle of the shock wave depends on the sound speed in the medium. So in this case, the temperature is higher, so the sound speed is also higher, and you produce a shock with a wider opening angle. In this case, it is colder, the sound speed is lower, and then the shock cone is almost aligned with the rarefaction zone that is behind the object.
So is this published work, or?
It is no. This is his bachelor project, but we want to make a paper of it later. So well, sorry, this is well. Of course, there is also my own work that I did with boson stars, with collaborations from Frankfurt. Okay, it is here. So well, this is my own work published in 2020 with collaborators from Frankfurt. We in the same way, so following the same concept, we wanted to see what is the astrophysical appearance of a boson star. What happens if you observe it? So we were thinking that something very simple would happen, so that all the matter would accumulate in the center of the star, and we would have a bright spot. But actually, we discovered an unexpected magnetohydrodynamic effect. So it turns out that the standard theory of accretion disk say the main mechanism for transporting angular momentum in accretion disk is the magnetorotational instability. And in order to have this instability operating, you need to have a rotation velocity profile that is decreasing with radius. It turns out that in general, for the inner edge of accretion disks, the rotation velocity is normally very close to the geodesic, to the angular velocity of circular geodesics. So specifically for these stars, we have the peculiarity that there is a maximum in the angular velocity of circular geodesics at some finite radius. And this is interesting because it means that while the magnetorotational instability will operate in this region, it will be suppressed in this other region where the profile is increasing with radius. So well, we made an actual simulation. Just sure.
So in the center, it doesn't rotate.
In the center, in principle, I think it should not rotate, but what you see actually is that it rotates a bit. So what we see is actually this happens in reality. So one has this. These are ray trace images of a black hole, Schwarzschild curve, and this is the case of a boson star. And we see the effect happening. There is a dark region that one can associate with a shadow, but it's not a shadow. It's actually just a lens image of this evacuated region where matter cannot accrete because it's stopped by the centrifugal barrier. So we try to test this and repeated the simulation for a case where the method didn't have this maximum, and this is what we obtained. So it's indeed, so when the instability operates, the matter reaches the center and starts glowing.
These are non-rotating boson stars.
These are non-rotating boson stars.
And it still has centrifugal potential.
Yes, I have, because it is a centrifugal barrier, but for the accretion flow that is rotating.
And not from the star.
Exactly, not from the star.
Okay. So you have some kind of matter around and you are simulating on top of this metric of an rotating model star.
Exactly. So the assumption is that the plasma doesn't affect the metric of the boson star.
And is there some assumption on the interaction between these particles that forms the star and your magnetic fields, or it's fine putting it?
No, that would be very interesting because in principle, so scalars, like for example, axions could interact with the magnetic field. But what we are assuming is that this is just plainly dark matter. It doesn't interact besides gravitationally. So, well,
Can I ask a question?
Sure.
Actually, two. So in the image that you showed us before, that used the PhD paper for essentially there is a star, you have a boson star, and actually it didn't have an effective shadow in that case, and you claim that you ruled out that kind of model. So I guess you're talking there about a model that doesn't have this feature, right? Okay, and well, it seemed to me the claim that was being made there was a bit too generic. Anyway, so then the second thing is, how likely is it that in a real astrophysics situation, this magnetorotational instability is really the driving mechanism to transport angular momentum? Because this mechanism here relies on that. Right. So are there other alternative mechanisms to carry the angular momentum? And then, well, this effect wouldn't be present because here it's relying on that. So perhaps you could expand a little bit on that.
Sure, I guess I can tell you quickly. So maybe there are at least other two mechanisms that are considered to transport angular momentum in an accretion disk. So one is well, molecular viscosity, but for these very dilute plasmas, it is very unlikely that it produces a significant effect. Actually, when people have calculated well, what would be the accretion timescale for this, if the driving mechanism for angular momentum transport was molecular viscosity, and this is a time longer than the age of the universe. So for these dilute plasmas, molecular viscosity almost plays no role. And there is another, which is angular momentum transport via spiral shocks. I think this is something that is more worth considering because this is something that would happen if you have an accretion disk that is subject to perturbations and that is not completely symmetric. So one can have a spiral shock, and then this would also help transporting angular momentum.
So would you expect that in a realistic situations, these several mechanisms would be there, and then therefore, then the conditions of the plasma will determine which one is actually carrying most of the angular momentum, and say that this last mechanism that you were saying could, just transport the angular momentum in spite of the inability of, the magnetorotational instability being unable to because of this feature?
I think yes, that is possible. But unfortunately, for the argument of ruling out these kind of boson stars, I think that would be less in favor of boson stars, because if there are more mechanisms that
no. Yeah, sure. No, I understand that. Well, one should consider all possibilities. But just a final question to kind of close this. So when you do your simulation, say with your back code, and I guess you see angular momentum being driven towards the inner region. So in that case, which mechanism is actually leading this transport?
Well, in our simulations, I think we see very clearly that this is mainly the magnetorotational instability.
And that has to do with the conditions of the plasma, because the code will be able to include the other effects.
Right.
If the conditions of the plasma.
Exactly. Yes, it is because of the conditions of the plasma, and I think it's also very much because of the initial condition that we use. So since the initial condition that we use is very symmetric, we will never have something like a spiral shock in this kind of simulations.
So if you do get a spiral shock, that's the term. So then have you analyzed any case where you have kind of this effective shadowing in that scenario?
I haven't. That would be interesting. I am analyzing scenarios that deviate from this nice symmetry in other contexts. So previously, years ago, we also in Frankfurt we did a case of a recoiling black hole that came as a result of a merger of black holes that had some peak. And in that case, you have a black hole that has some relative velocity with respect to the accretion disk, and you form a spiral shock. And in that case, even if it was pure hydrodynamics, you could see some accretion because the angular momentum was transported by the shock.
And for the boson star case, so how, so you said if you start with a highly symmetric accretion disk, then this is unlikely to produce these shocks, right? So how asymmetric would the initial data need to be in order to see this?
This is a difficult question to answer. I think one would need to try, well, to check by trial and error.
But it's not easy, I guess.
No, I think it's not that easy with the simulations.
In the example you gave, it's a black hole.
Yes, I know.
You need a strong perturbation, like
Exactly, you need a strong
very
perturbation.
strong. So I would, the other black hole could be that perturber. But in a situation where it's isolated, it's harder to see, right?
Yes, that's correct.
This effective shadow that you get happens in every theory, or is something that depends only on the maximum of the angular velocity happens in a region far from the origin? I mean, it's something that depends on the angular moment or on the angular velocity, on the model.
I think it should depend more on the space-time model, because after the rotation, the rotational instability starts operating, it redistributes the angular momentum, and more or less regardless of the angular momentum profile in the initial condition, it makes it resemble to that of circular geodesics. Yes.
Shakespeare, what are these model A and B? How general are the results?
Right. So all of this is for the family of mini boson stars. So the simplest family. And the difference between model A and model B is just that one has this feature and the other doesn't have it. But they also are different because model A, the one that has it, belongs to the family of the unstable boson stars, which is in blue here. And the model B that doesn't have it belongs to the family of stable boson stars. So interestingly, for mini boson stars, all of those that have this feature are in the unstable branch.
So one of them A is mini boson stars, those have interaction.
Exactly, and those are without interaction.
And B?
Well, B is also the same, but on the unstable branch.
Self-interactions, but these, they are all the model, it's in our paper, Eugene. So
Yeah, but
there's all the model without self-interactions. One is in the stable branch, that's where you don't see the shadow.
but you have phi at 0, you see, and they superpose. That's why I'm confused on the x-axis.
It's the scale likely.
So what I did
So the central value of the scalar.
Yes, yeah.
Yeah, he's saying because you label the boson star by phi at tau equal to 0. They seem to overlap over there, but that's likely because of the scale.
I see. Okay, you mean these two curves?
Yeah.
So these are different things. So the one is yes, I'm sorry that I should keep only one of the curves for the presentation, but one is the actual value that you have this, and the other is the size of the lens image.
Okay, so now I understand, yes. No, I'm confused by what they are different models.
Yes.
You put the central value of the star.
No, but it's so one is the size of the effective shadow for electric star, and the other one is just the radius. Right. So, but this is this question about the stability are very interesting because those also coincide very much with what I wanted to say in the next slide. So. For boson stars, we see that there is no, there are no stable models that have this feature. But actually, in a very interesting paper by this group, it was shown that there are other objects, proca stars, for which there are stable members that produce this feature. So, in a project also in collaboration with Carlos, and which was the master project of a student in Mexico, Jose Carlos, who you can see here. We try to see what happens if we indeed take these solutions and put them in a space-time with plasma and see if it indeed reproduces what we see. Interestingly, we see that for the case of 2D simulations, the behavior agrees very much with the prediction. So this is the simulation of a black hole and one of these proca stars after 5,000 gravitational timescales, and we see that indeed we have this evacuated region here, more or less at the location predicted by theory that was 6 gravitational radius. However, well, we wanted to see also in a realistic scenario what happened in 3D because physics changes. We have also the possibility of having non-axisymmetric modes. And this is what I want to show you in the next slide. So here we have an initial simulation. It is viewed from the top. It is very slow. The way how this updated, but we did see this the evacuated region at the center surviving for some time, but well, it doesn't stay there forever. If we look at the rotation profile, which is here shown in blue versus the one of circular geodesics that is shown in yellow, we see that turbulent perturbations in the velocity are actually too big compared to the height of this maximum. So it is very likely that what happens is that it is not. So these perturbations are too high compared to this bump in the profile in order for the fluid to notice it. So in the end, when we have something like this, the profile becomes flat, even when the actual rotation profile agrees with more or less with that of circular geodesics, and we don't have this effect. So we're still studying this. Is a work in progress, but well, we see that in order for this process to happen, there need to be more things in conjunction. So well, unfortunately, this speaks not so good about horizonless compact objects as black hole mimickers. But actually, well, this is something that we could already see a bit from the EHT results. So also the fact that there is such a big coincidence between between objects that are separated by orders of magnitude with curved black holes, well, means that likely it is not an object that has a scale as boson stars or Broca stars. So it is possible that we have to see for more subtle changes. And in fact, there are many solutions that we can explore as black holes surrounded by scalar curve. So we still don't know the actual deviation from curve up to a precision of 10%. So it is possible that we can still, for example, weight how much scalar curve is or Broca curve is allowed around these black holes. And in this, we hope to have, yes, maybe
yes,
for.
So I'm not sure, can you explain again what are these curves here? So I was expecting to see the maximum of the angular velocity, but so you are saying that flat line is actually a small maximum.
Exactly. This is the rotation profile of circular geodesics and has a maximum around 6, but this is very, so it's not so noticeable.
So
this
what
is
solution is this exactly?
This is
the solution we study now.
Okay, that's correct. So this is a bit hidden by the logarithmic scale in radius. So the maximum maybe is not as flat as is shown here, but it is flat compared to the perturbations in angular velocity. So probably the conclusion is that maybe we need to be more subtle in order to find when this effect really happens.
So the key point here is that you don't form kind of stalled accretion.
Exactly.
Radius.
Yes, and so probably it doesn't matter only that there is a maximum, but it also matters well how big is this maximum compared to the perturbations due to turbulence.
But that's not terribly surprising, is it? Because somehow realistic physics always has some sort of fluctuations, the real environment. So if you have, I mean, I was giving you this analogy of having an effective potential barrier, but if we have anything that oscillates and if there's potential barrier runs too shallow, it will not block whatever fluctuations you may have. So in a sense, I mean, you've given, I think it's a fair description, and but perhaps it would be interesting to emphasize that in your scalar case, you didn't see this.
Exactly.
And therefore, you know, the real kind of finding is perhaps under which circumstances can it happen?
Exactly, yes.
And that's kind of the interesting question that lingers somehow.
So would it be correct to assume that this would depend on, since you said it depended on the perturbation scale, right? On the initial conditions for the disk. So
That's right. So in fact, this is very much what we were discussing yesterday. So the size of the perturbations that you have is related a bit to the geometry of the disk, no? So and to other conditions. If you have a high magnetic field, then it is likely that perturbation will grow quickly, and so they grow exponentially in the linear phase. But if you start with a higher magnetic field, they array faster to the saturated state of turbulence. So this can have an effect on this. And another thing is the thickness of the accretion disk. So the MRI turbulence has a maximum, well, it has a fastest growing mode that happens at a given scale. And if the disk is thinner than this fastest growing mode wavelength, then that mode will be suppressed, and turbulence will be driven by other modes that grow slower. So under those circumstances, I think that it's possible that if you make the disk thinner, you can well decrease the amplitude of fluctuations and see this effect again. So this is something that we want to test.
So if I understand correctly, so in principle you could hook up some initial conditions where this effect would be.
That's what we think at the moment. Right. Yes. So, but well, as I was saying, well, it is possible that in the end, maybe horizonless compact objects are not what we want to constrain in the end, but maybe we want to have some higher, we want to see more deviations from the black hole solution. No? For example, to find what is the amount of scalar hair, or if the black hole has some extra charge, etc. And for that, we need extra precision observations. And indeed, there are plans to have observations with extra precision. These are the plans to build what is called the next generation event horizon telescope. So, well, this is so the science becomes every time more interesting, and then, well, we also have a bit more. There's a bit more funding to do other experiments with this. So so this project plans to include some more stations to the already existing array of the Event Horizon Telescope. This planned expansion will potentially improve resolution, also dynamic range, that is the ratio between the brightness and the less bright pixels in the image. And is also expected to go to higher frequency, also improving the resolution and adding the possibility to observe at multi-frequencies. And well, just as an example, you can see here that the eastern part of the arrays has a bit more stations than the eastern part, and this results in losing the ability to generate images with both of the sides of the array. So one could say even that we are only using half of the array to make images. Well, it's not extremely correct, but so we are using the array to some extent to half of its potential. So and I just wanted to show you the change by adding a station in Africa, in Namibia. So this is how the eastern part of the HT looks now. If you will just consider it to produce an image of Sagittarius A star, but as soon as you include this new station, you see something that will appear soon, something like this. So this means that if we are able to do more high resolution images with more parts of the array, in principle there is a potential to also study the variability in a more precise way. We could see if there are, especially for Sagittarius star, where it changes in the scale of minutes, we could see well how it moves and this will be able to make movies of the gravitational flow, which is a very exciting possibility. Another possibility.
Can I ask you, this station in Namibia exists already, or is this?
It doesn't exist. So at the moment, well, some members of the collaboration are looking for funding to build this station. But also the plan is to bring some dishes that have been deployed in another observatory and ship them to a mountain in Namibia that is called Gansberg, and just so put the station there. So this is a plan that will happen like in the next decade, right? And well, so another exciting prospect of the NGHC is that there are more sources that will become accessible. And one very interesting possibility is the potential for the discovery of supermassive binary black holes. We will probably not be able to image their shadows, but we could see some effects of these binaries. And well, so this is where, for modeling the coupling between BAC and KDAT come. So one can use an approximation that is called the conformal thin sandwich approximation that neglects gravitational waves, and assuming that the black holes are sufficiently far apart for this approximation to work, one can simulate with BAC the binary in the frame of the binary. And we can see, these are some examples of jets produced from binary black holes. This is an equal mass binary, and you can see this very interesting braided structure for the jets. So they are moving like this. You can see these nice spiral shocks illuminated in Bremsstrahlung X-rays. And you can see also this image in proxy for synchrotron emission at 230 gigahertz that shows well the images of the two black holes together with a bright line emission that comes from the spiral shock. So in principle, we are starting to look how these binaries of supermassive black holes would look, and if we see some of these in the actual observations of the EHT, will be something really exciting. Yes, sir. Question.
If you have a moving black hole in some kind of environment, you might have some dynamical friction effect, in which matter basically piles up behind the moving object. In that case, if it's slowly moving, so dynamics is under control, could you see something like this on a single black hole moving and infer the dynamical friction using image data?
I am not sure about this, but well, for these systems of supermassive black holes immersed in a dilute plasma, I suspect that the dynamical friction would not be so important.
You might need something probably smaller.
I think that effect would be important, for example, in what are called common envelope systems. So where you have a black hole or a pair of black holes, let's say, moving in the interior of a star. So there, dynamical friction and also the angular momentum absorbed by the black hole would be probably important for the evolution of the system. But I don't know if there is a possibility to measure how big it is. But for these systems, I don't think that it will be so important. Right. So well, of course, these developments will be accompanied by also developments in other observing experiments. So very interesting one are the gravitational wave detectors. So the planned gravitational wave detectors in space are supposed to also observe binaries of supermassive black holes. So there is a potential for having there also multi-messenger astronomy. And well, this will help jump into the new topic in the presentation that I hope to cover fast because there is almost no time. And so this topic is that these simulations that are will be in a completely different regime. So it is things, for example, extreme mass ratio inspires pose challenges to the current numerical simulations because of the necessity to resolve with very high accuracy the small black hole, or there could be also possibilities like the existing gravitational waves from cosmic strings or domain walls that are efficient, for which the nuclear relativity community has not a lot of experience and is not as refined as the simulations of, for example, measures of black holes. So, well, this is when the next topic that I want to introduce comes. So this topic is trying to apply MHD technology into simulations in numerical relativity. I am doing this in collaboration with these friends from Trento, from Princeton, and we're from Germany. So the idea is the following. I hope to go quickly. I don't know how much time I'm allowed to exceed.
There is plenty of time to ask a lot of questions, so 10, 15 minutes.
Okay, that's perfect. So, well, the idea is the following. So gravitation, electromagnetism, and MHD have something in common, and this is the fact that when you express them in 3+1, they result in a set of evolution equations, but also a set of constraint equations. In the case of numerical relativity, the constraint equations are the Hamiltonian and momentum constraints. In the case of Maxwell equations, the evolution equations are those of Ampere-Maxwell and Faraday, and the constraints are the two Gauss laws for electricity and magnetism. And in MHD or hydrodynamics, well, there are the Euler equation that give evolution, but there are also constraints like the global conservation of mass, energy, and momentum, as well as the Gauss law for magnetism. So the way in which these constraints are dealt to in numerical relativity is by different approaches. So one approach is to do nothing, but this leads to unstable evolutions. Another approach is to add some multiples of the constraints to improve the structure of the equation, and these are the BCSN formulas. And there is also another approach that adds additional equations in order to propagate away and damp violations to the constraints. You can see here some of the results of applying this damping method here, and this is another. Well, what you can see here are all constraint violations in a simulation of a neutron star merger. But left panel is damping the constraints, and right panel is doing the BSSN evolution. And you can see that while the result is good, the violations of the constraints they are still in the order of 10 to the -4, 10 to the -5, etc. However, there is an additional way of taking care of the constraints that is using numerical electrodynamics or magnetohydrodynamics. And these are to build constraint preserving discretizations. So what you can see here is an MHD simulation of a system that is called the Orsak-Tank vortex. It's a magnetic vortex in which you can, well, never mind, you don't see the wood, but you can see the final state. And so it has, maybe if I try to play it again. Okay, well, never mind. So, well, this is a system that has magnetic turbulence shocks. Sorry.
Yeah, so I'll have to go in 5 minutes, but I wanted to ask you some, even before you show the movie. So my question is that these techniques, they work very well if you have a single unigrid, but not so well if you have adaptive mesh refinement. Can you say a few things about that?
Well, in MHD, they can work even if you have an adaptive refinement.
It does,
so
even in the grid boundaries and so on?
Depends on how you do it and the scheme for the mesh refinement. So there are different ways of doing mesh refinement. So if you do what is called box in box, it is likely that it will not work because things need to be very consistent. But if you do OC3 mesh refinement, as we do in the back code, then it will work very nicely. Actually, one of the papers that I made during the PhD is well, it's precisely about how we make constant preserving prolongation and discretization operators that work in GR and that are for well, MHD and constraint transfer. So this is so yes, they can work well in AMR for MHD. Well, what I wanted to show is that that even if this system is very has a lot of complications, as I was saying, shocks, turbulence, etc. The violations to the constraints. Now it doesn't change it more. Okay, and so the violations of the constraints here remain always to effective numerical zeros, so 10 to the minus 15, etc. And well, it turns out that this is not the only thing that is easier to do in MHD than in numerical relativity, that is preserving constraints. There are a lot of things that are much more simple in electrodynamics on MHD. So one is the constant preservation during evolution, but also getting constant fulfilling initial data. For MHD is extremely simple. You just initialize everything for a vector potential, take the curve, and the solution is immediately divergence free. But in GR, you need to make spectral solvers as scalar, and generally initial data has evolved to a full subfield. Advanced conservation of conserved quantities, getting non-Cartesian coordinates and obstructor meshes, n-body simulations. And the reason why this is the case is because the equations of MHD have several desirable properties that allow to make this easier. One is that they are first order, that they are flux conserving, and that they allow for constant preserving discretizations. And the reason behind all of this is actually geometry. So one can see that clearly by writing these equations in the terms of exterior calculus. So this is not the standard way in which MHD equations are written, but it allows for many of these desirable properties to arise naturally. For example, the fact that taking twice the exterior derivative of a one form gives zero ensures that all the equations that will resolve will be only first order. The Stokes theorem will also ensure that if you consider this as a flux, the discretization that will resolve will be flux conservative. And in fact, it is relatively easy to obtain constant preserving discretizations from formulating the equations in terms of differential form. So one takes the equations, integrates using the Stokes theorem, and then one turns the differential system in a system of algebraic equations for some integrated quantities. The price to pay is that now quantities are defined at different spatial locations. So you don't have everything at the cell center, but there are some things at the cell center, other at the cell faces, and even at the cell edges.
So, but so the method that is being used is the finite element method or the finite volume method?
Well, here I wrote finite volume method and constraint transport. It turns out that these have different names, but are actually the same mechanism mathematically. So both of them rely of integrating over some sums of the domain and converting equations to algebraic equations. Also, this so finite volume methods are very related to finite difference methods. Sorry, to finite element methods. Well, one can also do finite conservative finite differences, but that's another story. But so indeed, so these are very related to finite element methods. What is different is the way in which you do the reconstructions. But this is we can talk more about this another time. But it's just to this is not so important for the discussion. But right, so well, one can also then use this to obtain constant preserved discretizations. And then what we want to do is to write GR in the language of exterior calculus and try to repeat the same procedure that we use for MHD and for electrodynamics. In fact, we don't need to reinvent the wheel because there is already a formulation of GR in terms of exterior calculus. These are the ingredients of the, let's say, kinematic parts of this. These are equations that should be true for any manifold. These are the Cartan structure equations, the definition of the curvature and torsion forms, and the Bianchi identities, which arise just from taking the exterior derivative of the Cartan structure equations. And here is the dynamic part. I don't know what happened, but now it's lagging also on this side.
I guess you're putting the torsion to zero, right?
Yes, so indeed, at some point we need to put the torsion to zero. Right, so this is the dynamics part. This is governed by this equation that is called the Sparling equation, and the elements that are there are the Nestor-Witten form and the Sparling form. So the Nestor-Witten form is a collection of two forms, and the Sparling form is a collection of three forms that is related to many expressions for the energy momentum. Like the Einstein single tensor, etc., depending on which pullback or which coordinates, in which basis you write. So interestingly, so we have now something that is a exterior derivative of a two form that is equal to a three form from this side, and from the side of the kinematics part, we have the first Cartan structure equation that gives the exterior derivative of a one form and relates it to a two form. So this is, if one thinks of it, this is a structure very similar to the one that one has in electrodynamics. So one has a potential that is a one form, takes the exterior derivative to get a field strength, and one has also a two form that is the field excitation. These are related by constitutive relations. And by taking exterior derivatives, you get the remaining parts of the theory. So in gravitation, is exactly the same thing. So one has, instead of a single one form potential, one has four potentials that are the one form basis in the manifold. One takes exterior derivative to obtain commutation coefficients, and on the other hand, there is a Nestor-Witten form that gives the dynamics part. These are connected by the fact that both this and this can be uniquely written in terms of the spin connection. So this that relates the field excitation with the field strength plays the role of the constitutive relation in electrodynamics, and this is very related to the discussions that we had at lunch. So we have a theory that resembles very much electrodynamics, but where the complication or the nonlinearities are hidden in the constitutive relations. So we can just express these equations in 3+1 form, and we get a system that looks very much like electrodynamics, but it's actually linear. So we have the first Cartan structure equation, looks as the definition of the vector potential in electrodynamics. We have the first Bianchi identity, and it looks its evolution part as the Faraday law, and its constraint part as the Gauss law for magnetism. We have the Sparling equation that looks exactly, or that is equivalent to the Einstein field equations and looks exactly like Ampere-Maxwell law, and its constraint part, that are the Hamiltonian and momentum constraints together, looks exactly as the Gauss law for electricity. And we have the conservation of total energy momentum that looks exactly like as the conservation of charge in electrodynamics. So this is no approximation, it's exact. It's not as gravitomagnetism, but it's just another way of writing the full Einstein equations. And it has, and here, well, to close the system, we need to have the constitutive relations that acquire this form. One also needs to have an expression for the gravitational energy momentum that we find here, and an equation for the gravitational energy momentum current. And well, the interesting thing is that having a structure that is almost the same as the structure of electromagnetism or of MHD, one can recycle the same numerical techniques that are used in this and apply them to numerical relativity in order to have, well, machine precision preservation of the constraints, and also in order to have all the nice properties that the system well, that the other system have. So, well, just as a summary of this last part. So this formulation of so just to summarize this last part, this formulation that to obtain is suitable for high resolution shock capturing techniques as NHD, and also for finding the element methods. That is also useful to well, find initial conditions. It is easy to apply to curvilinear coordinates and to unstructured measures, just as electrodynamics, and that admits a natural preserving machine precision discretization, which is the same that is used for electrodynamics and that was derived for in several years in the 70s for problems of electromagnetic waves propagation from antennas.
So have you applied this, or are you in the process of?
I'm in the process. So we published this paper with just the outline of the method, and we are now working on numerical implementation. But so we are working now in another paper that is so all of this can be also derived from a Lagrangian formalism, and then one can also generalize this to other theories of gravity. The easiest one is teleparallel theory, because the action looks very similar to how the action looks when written in these variables. So one can, in principle, also apply all of these technologies to alternative theories that involve torsion. But this can in principle be applied to have a numerical implementation with high precision waveforms, because one preserving well the contrast, one can evolve the system for extremely long times. So for very large spirals, let's say of supermassive black holes, one can do this, and it could also be possible to simulate systems that cannot be simulated currently, because the violations to the constraints just grow too quickly. For example, superradiance, also the anti-de-Sitter instability, embries, and even chaotic three-body interaction, because we can do the same that we do in electrodynamics and treat black holes, let's say, as point particles.
But you can ask it, so, but say boundary effects become a nuisance in that case. I mean, if you can control the constraints, but you still have the fact that you have a finite grid, and that introduces some spurious perturbations, and therefore the level at which you're preserving the constraints via this method is spoiled by other nuisances. Isn't that true? Or
yes, that is true. So there are some other nuisances, not only boundary conditions, but for example also in hydrodynamics. If one wants to couple this with hydrodynamics, let's say to study the evolution of neutron stars, probably what would constrain the method more would be the inability of Jeremy codes to simulate vacuum, because normally, in order to avoid simulating vacuum, we introduce very low density matter, and this would of course also break the Einstein constraints, no? Because you will be matter will be appearing out of nowhere. But even in this case, I think the fact that it can improve, it can improve.
Sure. Yeah, I was being devil's advocate.
Right. So, well, just to conclude, because also I have taken a lot of time, this is the message that I would like to take away. So, well, I would like you to take away. So, first, that we need NHD because the interpretation of the state-of-the-art observations needs to take into account the effects of plasmas that exist in the real universe. So searchers for new fundamental physics must be aware of this, of the fact that the universe is full of plasma, and that this is not the only way in which magnetic hydrodynamics can contribute to the search of the new fundamental physics, but it also can contribute by recycling the methods that are used there, and that can be and that these methods can be applied also into other fields such as numerical relativity. And so, well, that's all that I wanted to say. I'm sorry for taking so long. And thank you.
Thank you, many thanks, Kevin. Hector, for your interesting talk. Guys, it's 1 hour and 10, so I would say one last question fast, and then we can talk later.
Well, if there's someone that wants to ask, please, otherwise I can ask.
I can't answer.
No, you go ahead.
Okay,
You go ahead.
someone
I'll
else
talk
wants to
to-
ask a question?
I'll talk to.
We have time for two.
Yes.
I was just wondering, you show us the boson stars, so systems in which you have an extra scalar field that is the protagonist of the central object,
Right.
and you are evolving all your equation on top of a metric. So have you thought if can be done to look at, for instance, scale magnetized black hole? So you are looking at a solution that you're already using, just that you are adding some magnetic lines on that and trying to see if this might have an impact of this on the exterior magnetic field. I don't know if this makes sense, if this can be implemented numerically, but it can have an impact. But
What do you mean by Kerr magnetized?
so there are some solutions in which you have infinite magnetic lines, so you should take some kind of cutoff, but basically it's a Kerr black hole or a Kerr-Newman black hole with lines of magnetic fields. And maybe this can be implemented to do the first step beyond looking at how extra fields interact with your disk. I don't know if this can be done.
Yes, well, of course, that can be implemented as an initial condition. So I think for black holes, this has not been done, or maybe I have seen some simulations of what they call balding black holes. So they have magnetic hair, and then they lose this hair, and so the simulations show how this happened. This was work done by Sasha Shekovsky and others. So this has been done already with Yarmeshdie code. So I think that's possible. And another place where I have seen an object that is initialized from the beginning with magnetic fields is in simulations of neutron stars. So the backcode has also been used for those systems, and indeed you can have some magnetic field as initial condition, and then see how the plasma interacts with that magnetic field that was already there. So I would say yes, it is possible.
Well, I mean, it's a very generic question, but perhaps for the benefit of other people. And for instance, in this last part, you focused on how you could computationally improve your evolutions of, say, a plasma on top of a black hole, eventually even something more accurate. But my question is always to people that do this: how good is our knowledge of GRMHD and of plasmas in the real universe? So you've been working on this for a while. So, I mean, what are the caveats in the models that we are using now to model real astrophysical systems? What's your kind of impression of where things can still be improved? If you have a strong impression about this, where is it that our knowledge is lacking something? What's your impression about this? It's very generic, but I think it's kind of relevant.
No, this is actually a question about which I wanted to talk about. So I think so that well, the presentation was already quite long, but I wanted to add some work that I am doing currently. So, but well, let's start first from exactly the question that is. So at the moment, one of the main issues that we had at the Event Horizon Telescope in trying to interpret the the observations of Sagittarius star was to match the correct variability of the simulations. So we see that light curves at synchrotron are very are much less variable than what we see in our simulations. We also saw a bit that problem for MET7 that is more pronounced for Sagittarius star. And well, this is something that people is studying at the moment. So one possibility is that there are effects that are not taken into account. For example, effects from the fact that maybe the ideal fluid approximation is not the best approximation. So it can be that and actually it is known that the mean free path for ions in the galactic center is larger than the gravitational radius. So it is possible that plasmas never thermalize there, and then the MSG approximation is not such a good one. And So this could introduce some processes that dump the variability, like effective resistivity from the kinetic effects. So this is one thing that people is looking at. So maybe there are other effects that damp in some way the variability, that it produces something less variable as that we see. But something in which I have been particularly interested is in the fact that other simulations that are performed at larger scales, so Newtonian simulation and recently also one general relativistic simulation, show that if you simulate the stellar winds from where they are produced until where they reach the central black hole, you see accretion patterns that are very different from what we have in our simulations. So we always start by very symmetric torus in which turbulence is more or less will introduce some disorder, but not a lot of asymmetry, and that already starts from being bounded to the black hole. But these simulations show a very different picture. So they show that the time scale for the matter to circularize is larger than the time it takes to get to the black hole. So it is likely not circularized. The structures that are formed are much more asymmetric. And also the energetics of the plasma are different. So it is not bounded matter, but since it came from very far away, this is still unbounded. So well, these simulations have predict that there are more different properties and even a broader parameter space in initial conditions than what we typically use. So I would say those are that maybe those are the main open problems for me for the regarding the modeling of plasmas close to supermassive black holes. One is this, so whether there are non-ideal physics that we need to include. Another one is the problem with initial and boundary conditions of simulations. If in reality it should be something completely different than what we use.
Okay, that's very interesting. Thank you for your answer.
Okay, guys, I think that's all for today. Another round of applause.